Microscopy is a technique which is used to observe the specimens which are too small to observe with human eye. There are various techniques or various microscopes that can be used for this purpose. Today in this module, we will study about the types of such microscopes, their advantages and disadvantages. What is microscopy? Theoretically, a microscope is an array of two lenses. Why do we need microscopy? As cells and their organelles, few living organelles, are too small to be seen with the human eye, they can only be seen with the aid of a microscope. So, to observe such minute structures, we need microscopy technique. In this image, we can clearly see the different parts of simple microscopes like objective, eyepiece, light source, etc. Before using this technique, it is very important to know about magnification and resolution. Now we will see what is magnification and what do we mean by term resolution. Magnification can be defined as the capacity of microscope to maximize the image of an object than its real size. This magnification is dependent on magnification of objective as well as magnification of eyepiece. It can be derived by using formula magnification is equal to magnification by objective lens into magnification by eyepiece. Concept of magnification which is denoted by capital M. Magnification of microscope is equal to magnification of an objective into magnification of an eyepiece into magnification of intermediate factor. For example, if magnification of an objective is equal to 70x and magnification of an eyepiece is equal to 10x, intermediate factor is equal to 1x, then overall magnification will be equal to 70 into 10 is equal to 700x. We should also remember very well that maximum magnification does not mean maximum resolution. The details seen from the microscope depend on the resolving power of a microscope, which is its resolution. So, resolution is the capacity of microscope or its lens to distinguish two separate objects or points. Therefore, resolution can be defined as the ability to distinguish between two points on an image. This resolution or resolving power of a microscope is ultimately limited by the wavelength of light, which is 400 to 600 nanometer for visible light. Now we should remember certain points like using a microscope with more powerful magnification will increase the size of the image but will not increase the resolution. When an object is much smaller than the wavelength of the radiation being used, the waves are not interrupted by an object. Therefore, the object is not detected. To improve the resolution, shorter wavelength of light is needed. As in visible range, blue light has the shortest wavelength, microscopes sometimes have blue filters for improvement of resolution. Wavelength of light is used as major factor in the resolution. Shorter the wavelength, greater will be the resolution. Microscopy is a technical field which uses microscope to view the object and areas of objects which cannot be seen with the help of naked eyes, that is, objects that are not within the resolution range of normal eye. There are three well-known branches of microscopy: optical microscopy, which include fluorescence microscope, electron microscopy, for example SEM or TEM, and scanning probe microscopy, X-ray microscopy, which is very less used. Optical or light microscopy involves passing visible light transmitted through or reflected from the sample through a single or multiple lenses to allow a magnified view of the sample. The resulting image can be detected directly by eyes, imaged on the photographic plates, or can be captured digitally. Optical and electron microscopy involves the diffraction, reflection, or refraction of radiation incident upon the subject of study, and the subsequent collection of this scattered radiation in order to build up the image. Scanning probe microscopy involves the interaction of scanning probe with the surface or object of interest. The single lens with its attachments or the system of the lenses and imaging equipment along with the appropriate lighting equipment, sample stage and support makes up the basic light microscope, light or optical microscopy. This is the oldest, simplest and most widely used form of microscopy. In the specimen is illuminated using natural sunlight or artificial light using glass lenses. The image is seen by an eye or can be captured on photographic film. In this type, the specimens can be living or dead, but they often need to be stained with colored dyes to make them visible. Many different stains are available that stain specific parts of the cell such as DNA, lipid, cytoskeletons, etc. The light microscope we use now are compound microscopes, that is, several lenses are used to obtain high magnification image. Light microscopy has a resolution of about 200 nanometer, which is good enough to see the cells but are not sufficient to observe the details of cell organelles. With the resolution of about 200 nanometers, cells can be observed, but the details of the cell organelles cannot be observed properly. For example, fluorescence microscope has a resolution of about 10 nanometer, while interference microscope has a resolution of about 1 nanometer. Fluorescence microscope. When illuminated with high energy, certain compounds emit light of lower energy, which is known as fluorescence. In fluorescence microscope, we use this property to localize various compounds. This method can be extremely sensitive, allowing the detection of single molecules. Various fluorescent dyes are also available, which are also used to different chemical compounds as well as structures. We can also combine antibodies with fluorophore in immune staining techniques. During this technique, commonly used fluorophores are fluorescein or rhodamine. For this purpose, the antibodies can be tailor-made or specific chemical compounds can be synthesized. This technique is very useful for examination of biological samples. It facilitates identification of particular molecules in complex structures, for example cells. It can locate the particular molecule in the structure. It is also used to study the biochemical dynamics. Drawback of fluorescence microscope is it requires chemical labeling. Advanced example of fluorescence microscopy is two-photon or multi-photon imaging. Two-photon imaging technique enables greater excitation, light penetration and background emission signal is reduced, which also allows the imaging of live tissues up to very high depth. Super penetration multi-photon microscopy is also a recent development which allows imaging at greater depths than two-photon or multi-photon imaging. In microscopy, preparation of slide sample is also required. It is done using following methods. Step 1. Fixation. During this, preserved material is preserved in lifelike conditions using various chemicals. This will not allow the specimens to distort. Step 2. Dehydration. After fixation, ethanol washes are given to remove the water from the specimen. This is mainly important for electron microscopy as water molecules deflect the electron beam and interfere with the image formation, making it blur. Step 3. Embedding. In this step, tissue is embedded in the wax or resin to facilitate cutting of sample into thin sections. Such sections are cut with the microtome or an ultramicrotome. Step 4. Staining. Most of the biological material is transparent, therefore it needs staining. Staining increases the contrast between two structures. Different type of tissues are stained using different stain. Methylene blue is often used for animal cells, while iodine in Ki solution is used for plant tissues. Step 5. Mounting. Mounting is the step necessary to protect the sample. Limitations. Optical microscopy can only take images of dark or strongly reflecting objects effectively. Compound optical microscopes have many limitations with respect to the ability to resolve the fine details. It is dependent on the properties of light and the refractive material of lenses. A lens magnifies by bending light. Dark field microscope. Dark field microscope is used in case of objects lacking in sufficient contrast and are difficult to observe. It is used to observe live unstained samples. In dark field microscopy, an opaque disc is placed under the condenser lens to view a specimen. Due to this, only light that is scattered by an object on the slide can be reached to the eyepiece, due to which everything present on the slide gets visible as bright white against a dark background. Pigmented objects are often seen as different colors than the colors of object, which is called as false colors. In this, better resolution can be obtained as compared to bright field viewing. This is the low cost alternative for phase contrast optics. The contrast and resolution obtained with inexpensive dark field equipment may be superior to the student grade phase contrast equipment. Dark field microscope can be used for initial examination of suspensions of cells. For example, motile cultures, blood cells, bacteria, yeast, cells and tissue fractions, chloroplasts, mitochondria, etc. Differential interference contrast microscope. Many biological specimens cannot be effectively visualized using ordinary bright field microscopy. This is because of their images which are produced with very little contrast. In such cases, differential interference contrast microscope is an excellent mechanism for rendering contrast in transparent specimens with the help of differences in the index of refraction of specimen components. An advantage of interference derived contrast is that the object will appear brightest against the dark background. Those regions of specimen where the optical path increase along the reference direction appear bright or darker, while regions where the path difference decreases appear in the reverse contrast. As the gradient of the optical path difference grows steeper, image contrast increases dramatically. Phase contrast microscope. This was first described in 1934 by Dutch physicist Frisch Zernike. Phase contrast technique was introduced for testing of telescope mirrors in 1930s. After several years, it was adopted by Zeiss laboratories, which brought it into the commercial microscope stage. This optical technique enhances contrast, which helps in producing high contrast imaging of transparent specimens. For example, living cells, subcellular particles, microorganisms, etc. Very important advantage of this technique is we can observe living cells in their natural state without killing them. When most of the living biological specimens are virtually observed in the optical microscope under bright field illumination, they are transparent. One has to reduce the opening size of the condenser iris diaphragm for improvement of visibility and contrast in such specimens. But this also causes loss of resolution and introduces diffraction artifacts. Large extended specimens are also easily visualized with phase contrast optics due to diffraction and scattering phenomena occurring at the edge of these objects. Mechanism. When an incident wavefront of an illuminating beam of light passes through a phase specimen, it gets divided into two components. Component 1 is primary component, commonly referred as the surround or S wave, which is undeviated. This does not interact with the specimen but passes through and around the specimen. Component 2, deviated or diffracted spherical wavefront, that is D wave. This scatters over many directions and passes through the full aperture of the objective. When surround and diffracted light waves enter the objective front lens element after leaving the specimen, they are focused and are combined at image plane to produce a resultant particle wave, that is P wave. If there is a significant difference in the amplitudes of particle and surrounding waves in the intermediate image plane, then the specimen acquires a considerable amount of contrast and is easily visualized in the microscope eyepiece. In other cases, the specimen remains transparent and appears as same as ordinary bright field conditions. It facilitates the observation of unstained biological specimens without significant loss in the resolution. Due to this property, it is widely utilized for examination of dynamic events in living cells. Phase contrast microscopy is useful in observing transparent, unstained live cells. This technique is superior to bright field optics as fine details which cannot be observed under bright field optics can be observed here in high contrast. But in case of thick samples, this technique is not ideal as they may give hollow effect and appear as distorted. Electron microscopy. Electron microscope was developed in 1930s. It uses electron beam instead of light source to observe the image. Because of much lower wavelength of electron beam than that of the light, resolution is far higher. Electron behaves like waves and can easily be produced. It can be produced using hot wire. They can be focused using electromagnets and can be detected using phosphor screen or photographic film. A beam of electron has an effective wavelength of less than 1 nanometer. Therefore, it can be used to resolve small subcellular ultrastructures. The development of electron microscope in 1930s revolutionized biology, allowing the observations of organelles such as mitochondria, endoplasmic reticulum, membranes in the details for first time. The main problem with the electron microscope is that specimen must be dead so that they can be fixed and viewed in vacuum. The specimen can be damaged by electron beam and they must be stained with an electron dense chemical, for example heavy metals like osmium, lead or gold. Initially, there was a problem of artifacts. For example, some structures were observed due to preparation process and were not real. But Improvements in the techniques have eliminated most of these. There are two kinds of electron microscopes. Transmission electron microscope, which is known as TEM, or scanning electron microscope, which is known as SEM. TEM or transmission electron microscope works much like light microscope. It transmits the beam of electrons through thin specimen and then focuses the electrons to form an image on the screen or on the film. Electron beam is created using cathode, which is generally a tungsten filament, and it involves high voltage. The beam is focused using electrostatic or electromagnetic lenses. This is most common form of electron microscope and has the best resolution. As these electron needs to pass through the sample, taking section of the sample is necessary for the image to produce. After the beam hits the sample section, the electrons and X-rays are ejected from the sample. The special variation gets magnified with the help of electromagnetic lenses. The detector collects these rays and converts it into the signal and then into an image. The resolution limit is around 0.0 nanometer. The scanning electron microscope scans a fine beam of electron onto a specimen and collects the electrons scattered by the surface. This has poorer resolution, but it gives excellent 3D image of surfaces. Scanning electron microscope, at the top of an instrument, electron gun is placed to produce a beam of electron. The vertical path through which the electron beam is passed is filled with a vacuum. It travels through electromagnetic field and lenses followed by the sample. A beam of electron is passed over the surface of the sample. The sample is coated in heavy metal and electrons are reflected off the surface of these coated samples. Reflected beam of electrons are focused on fluorescent screen in order to make the image. This gives the outer structure and therefore larger, thicker structures can also be observed in SEM, as the electrons do not have to pass through the sample to form an image. SEM has lower resolution than that of the TEM. It visualizes details on the surface of the cells, particles, and gives very nice 3D view. It allows researchers to examine a variety of specimens. SEM has allowed researchers to examine much bigger variety of specimens. Its magnification is in the lower range than that of the transmission electron microscope. There are few advantages of SEM over traditional microscopes. They are as follows. It has large depth of field, allowing more specimens to focus at a time. It has higher resolution, which allows the magnification of close-spaced specimens at high level. It gives strikingly clear images. As vacuum conditions is included in this technique, all the water must be removed from the sample by vaporizing it, due to which it needs a sample preparation procedure. X-ray microscopy. It is used to produce enlarged images of sample. The samples are illuminated with X-rays, and there are two main principles of microscope. One, full field microscope, and two, scanning microscope. In scanning microscope, the sample is illuminated with bright, well-focused spot scanning over the sample. The detector then measures the total intensity over time coming from currently illuminated spot on the sample. The image is calculated from this data when scanning process is finished. Advantages of X-ray microscopes over other type of microscopes. X-ray penetrates the matter far easier than visible light, giving the inside image of the sample which are opaque for visible light. X-ray microscope can achieve higher optical resolution than microscopes using visible light, as wavelength of X-ray is much shorter than the visible light. Limit of optical resolution of X-ray microscope is far below than the diffraction limit of microscopes working with visible light. Scanning electron microscope in comparison have a high image resolution, but they need vacuum proof samples with metallic or metallized surfaces. Scanning electron microscopes are unable to image the inner of the sample. Scanning probe microscope has wide range of applications. For example, in topography or atomic structures, in magnetic or electric fields, or in surface temperatures. Based on our objectives, we can choose any of these techniques and we can study the specimen.